and we are going to examine the name of the course, the words here, the introduction to quantum computing. And I believe there's no problem with understanding the words introduction and the and to, but the words quantum computing may be unclear. So let's explain them, and we start with computation or computing. How would you define this term, this word? If you reflect a bit on this notion, you may find it difficult to define. What does it mean to compute? It is among those words which we take for granted, but if a child asks us to define it, we have problems with that. And actually, with children, it is easier. We can, instead of an explanation or a definition, we can provide some examples. But here, it doesn't work. We have to generalize all these examples into some short and simple definition, like this one. The computation is a physical process, finite in time, with a fixed and distinguishable set of states. The set of distinguishable states. Now, you understand that there are many other definitions of this term, of this word, computation. Why I do like this the most, and why I choose this for this course? Because first, it amplifies the notion of a physical process. We often forget this, that the things that compute often and usually rattle, click, and make different noise like this. And they usually, not even usually, always, they consume or transform, if you want, energy. Now, this notion of states. There are many processes in the world which rattle and consume energy, but if they then don't have these distinguishable states which we can identify, then we don't call them a computer. It is often told that computations transform or process information. To agree with that, we have to think again and to define this word, information. And I choose to connect this definition with that of a computational system of computations. Since the computational process has a fixed state set of distinguishable states, I choose the current state of the system to be the information it presents. And I choose the word interpretation here for a reason. Because you see on this slide two different systems. Both can store some information. And in some cases, we can say that these two systems store the same information. But how can we do that? These are very different systems. They have very different sets of states. How can we say that they store the same information? To do that, we have to invent some conventions about how we would interpret these system states, how would we read information from them. And to do that, we first have to define the notion of quantity of information. Because, for example, we might need to establish the fact that one system can store the information stored now by another system. And we may already feel that this notion of quantity is somehow connected with the number of states available for this system. The first mathematical description of this notion of quantity of information was introduced in 1948 by an American mathematician and cryptanalyst Claude Shannon. And the amount of information that can be stored by a system with n states was defined by his famous formula, the Shannon's formula, here. Here you can see the sum over all states of the probabilities of each state, multiplied by the logarithm sum base b of this probability. And we want this value to be positive, so this is why this minus here, because all the logarithms here are negative. Now, the probabilities come from physics, where this formula was introduced by Boltzmann to define the entropy of a system. And the physicists are interested in a much more general set of physical processes. But for computational processes, at least designed by human, all these probabilities usually are equal to each other. So for any I and j, probability of the state I equals to probability of state j, and everything is equal to 1 divided by the number of states, by n. And in this case, for the case of equiprobable states, we have the simplification of this formula. So instead of pi, we just write 1 divided by n, and logarithm base b of 1 divided by n. And we can invert this logarithm like this and to remove this minus. And now we have this sum of equal elements. There are n elements. So we can write it like this. And we can now erase this, and we have this logarithm. So the amount of information stored by a system with n equiprobable states is just the logarithm base b of the number of states. Now let's take a closer look at this value b here. Actually, it is a matter of convention, and the smallest natural base for the logarithm is 2. And if we take a system with only one state, we see it is 0, so the system with only one state stores no information. The next number is 2, so logarithm 2 equals to 1. And this is the amount of information, that the smallest amount of information that can be stored by a physical system. And Claude Shannon called this smallest amount of information with the logarithm with the smallest base. He named it bit, as a small piece of something in English. And now we can measure information in bits. Imagine a system which stores n bits. That means that this system has 2 in the power n states. And it is the same amount as the amount of integer numbers, which can be represented by n binary digits. So we can now enumerate these states. We can assign each state its number. And if we have 2 systems, each of them which can store n bits, and the states of these systems are enumerated like this, then we can map the states of different systems. And we can now say that these different systems store the same information. Let's consider an example. The system depicted here was never implemented physically. It was designed as a thought experiment by Hungarian physicist Leo Szilard. In 1929. So the system is like this. It is an empty camera with a partition, removable partition here. Which divides the camera into parts. And there is one particle of gas in the camera of the temperature T. And by the sides of the camera there are pistons which can be moved inside the camera, but they can't be moved outside because of these stoppers here. And we will distinguish two states for this system. The particle stays somewhere here in the left part of the camera. We will call this state 0. And if the particle stays in the right part of the camera, we will call this 1. So this system can store 1 bit of information. Okay, when the partition is removed, it is not actually a computational system, computational process, because we can distinguish these two different states. We can say in which part of the camera now we can find the particle. But we can do this. We can assign this system a particular value. To do that, we have to remove this partition, if it's not yet removed. And then we are going to compress the gas. For example, we want the system to represent the value 0. So we fix this piston, and we move the right piston on the left. So we compress our 1 particle gas. And we stop when this right piston reaches the middle of the camera. And we place the removable partition. Then we can move our right piston back. Now we are sure that the particle stays here in the left part of the camera. And this process took some effort from us, which equals to the constant, the Boltzmann's constant, the temperature of the gas, and the logarithm of the fraction of volumes. We decreased the volume 2 times, so this equals to 2. And this is how much work we need to assign a value. And this is a very interesting fact. To assign a value, we have to dissipate some energy. Let's do something else. Let's, for example, we now have this value of this bit equal to 0. Let's apply the NOT gate, which maps 0 to 1. How can we do this? We now have this state. Now we can move this right piston here to the partition. And this does not take any effort because we don't compress the gas. There's no gas on the right side. Then we remove the partition. And then we move both pistons to the right, like this. And the volume of the gas does not change. And when we place this volume on the right part of the camera, we place the partition again, and then we remove or move back the left piston. Well, we applied the gate node. We are now pretty sure that the particle stays in the right part of the camera, so the system stores the bit 1. And we did not dissipate any energy. We didn't do any work. So gate node, the reversible gate, does not take any energy in this system. Doesn't need any energy. And now assume that we don't need to store this bit anymore. What can we do? We can just, like in this case here, we can just remove the partition and let this particle fly all around the camera. But we can do something more clever or something more smart. We can put this piston back here with, again, no work. And then remove the partition and let this particle to push this piston back. So this compressed gas will give us this amount of energy back. And this operation is called erase. Now, what does it mean? It means that if we know in which part of this camera we now have a particle, we can transform this knowledge into energy. So the information, in some sense, equals to energy. Imagine that we didn't have this partition, and at each point of time, we can find out where this particle is. So we can place the partition and move the piston of our choice. So we can extract some work, some energy of this system. So the information, in some sense, equals to energy, and this is why it's often said that information is power. Bad news for Plato and Socrates, though.